Okay, now that we've introduced the idea of a well-posed versus an ill-posed problem, let's extend that to the idea of a well-conditioned versus an ill-conditioned problem. So we have this idea of conditioning now. So to introduce conditioning, it helps to just go back to square one again. We have 2 point charges here. We had an observation point here, but now suppose I have a second observation point maybe right here next to it. Now, mathematically, you might look at that and say, well, those are 2 distinct observation points, and they aren't exploiting any symmetry in the system. So technically, they are 2 unique samples in my scalar potential, and I should be guaranteed a unique solution because my matrix is still invertible. In practice, however, your intuition should probably be troubled by this, because obviously, I can't just squish these 2 observation points together arbitrarily, because eventually they will overlap with each other and you get an explosion in your matrix inversion. So you might then say, well, what happens if they're really, really close but not quite touching? How does that make things bad? How bad is that? Is it even bad at all? So for example, let's say these 2 guys here are something like, a nanometer apart. So mathematically, there is a distinction, but in practice, they might as well be the same position. Surely, that will create problems if I try and do this in practice. So to understand how this sort of situation might give rise to trouble, it helps to think about what happens in the real world when you try and take measurements like this. So I'll have here my phi1, and over here will be a phi2. And they're very close to each other, but not quite. So if I do this with a real world measuring device, I'm not actually going to get some precise value here. What will actually happen is I will have an estimate, say phi bar, of the value of phi at this position, which will look something like this, phi1 plus eta, where this eta is some Gaussian random noise, say, right? So no measurement is absolutely going to be perfect. In practice, there will always be some uncertainty in the measurement that you do because the environment itself will have some noise to it, or the measuring device will have some noise to it. Likewise, my second sample here will be phi1 plus phi2 plus eta 2. So some other little Gaussian random variable being sampled. So what happens when I insert this into my matrix vector equation? So remember, we had this idea of AX equals B, and ideally we would say X is equal to just A inverse B, like so. But now I don't really have the correct exact B over here. What I instead have is something that looks like this. I'm going to call this B naught, say, plus eta. So there's some noise associated with this thing. So when I try and calculate this, what I'm really going to get is A inverse times B naught, the true value here, like so. And then there'll be plus A inverse times my noise vector over here. So it's tempting to think, well, if I just have a little bit of error here, then that will imply a little bit of error in my unknowns over here. But the reality turns out to be very, very different than that, because this operation here doesn't just casually add a little bit of noise. And the underlying theory behind this is very, very complicated. But the results are actually very practically sound. And what happens is this thing sort of acts like an amplifier here on my noise. And the more ill-conditioned my matrix is, the more ill-conditioned this problem is, the closer these 2 little samples are to each other, the more this thing here will tend to amplify the noise in my results over here. So in effect, what will happen is I have technically a mathematically unique solution, but the more I squish these 2 samples together, the more this susceptibility to noise becomes a serious issue. So let's try and quantify that a little bit. The actual theory behind that turns out to be very, very difficult to quantify. But if you do just a simple test case, you begin to see kind of what's happening in your result. So let's just suppose I have something like the following. So here are my 2-point charges. Here's my 2 observation points. And I'm just going to place them, say, a nanometer apart. Okay, so what you'll get is something that kind of looks like the following with my system matrix: R11, R12, R21, R22, Q1, Q2 is equal to the following. And I have a 4 pi epsilon naught V1, 4 pi epsilon naught V2 plus noise and noise, like so. Okay, so when I invert the matrix, obviously you're going to see something that maybe looks like the following. Q1, Q2 is equal to this whole matrix inverse times my 4 pi epsilon naught V1, 4 pi epsilon naught V2. Sorry, it's a little messy. Plus, and then I'll get the matrix inverse again over here being multiplied by my noise samples over here. So what we're going to do is just focus on this term here and kind of ask what happens as these 2 terms here get smushed closer and closer together. So let's look at that right now. Remember that for the special case of a 2x2 matrix, the inverse is actually pretty straightforward to calculate. So I'm going to write this out now as the following. R11, R22 minus R21, R12 times 1 over R22 minus 1 over R12. And you get a minus 1 over R21, and then 1 over R11, like so. So this bit here doesn't really have any trouble, but you'll notice I have a singularity here. That is to say, as my distances all approach the same value, I approach an infinity here. That is, I get a 1 over 0, or something very close to a division by 0. So you can kind of think of that. So let's just draw out our situation here. Here's my 2 points. There's my R11, there's R22, and then there's R21 and R22 there. So as these 2 points get squished closer and closer together, this term here starts to approach 0, and I get a 1 over 0, or something very close to a 1 over 0. So in the limit, as these 2 things squish closer and closer together, the closer I get to a division by 0, which means this leading coefficient skyrockets to infinity. So what that means is my A inverse times my noise vector basically blows up to infinity as these 2 points here get very, very close. So that's the idea of that noise amplification as my matrix becomes less and less, or closer and closer to being singular, right? And so it's easy to see for the special case of a 2x2 matrix, but this is actually an idea that applies even as you go all the way out to the general case of an n by n. And like I said, the proof of that is very involved and very difficult, but you can see for a special case, it makes perfect sense. And then for the general case, you just have to think of that idea applying further and further, no matter what. So in effect, this is what happens when you create a very poor, it's not ill-posed, it still technically has a unique solution, but you aren't exactly creating very stable information here. The slightest little bit of error between these 2 little samples will blow up to create a huge, massive amount of error in my inverse calculation. So this is what we would call a poorly conditioned matrix. Like so, or you might even call it a poorly conditioned problem. That mathematically, it still works, it has a correct and exact solution, but the moment you start throwing a little bit of noise into it, that little bit of uncertainty in your noise suddenly blows up into a massive amount of error in your final calculation. So, fun fact, MATLAB actually has a interesting little command called cond. Okay, where you would simply actually just give it your matrix like so, and it will spit out a number, kappa, which is called the condition number. Okay, so that condition number is just a number greater than or equal to 1. So a condition number of 1 corresponds to the best awesomest conditioned matrix it is possible to have, which would usually be a diagonal matrix like this. This matrix has a condition number of 1. That is to say, it's the most perfectly conditioned matrix it is possible to have. If, however, I create a scenario like this, then my condition number might actually blow up to 1,000,000 trillion billion, right? So for example, in a very poorly conditioned matrix, you might see values as high as 10 to the 15th, say, or 10 to the 17th. And so what that means is technically it will still invert perfectly, but if you add the slightest little bit of noise into it, that little bit of noise blows up your solution and you no longer are able to create a stable inversion. And in fact, there's an upper limit to that still just by the fact that you're using a computer. Because in a real world measurement, you may have a tiny bit of noise, but that doesn't mean we can't, say, try and simulate a idealized system without any noise whatsoever. However, the simple fact of doing finite precision arithmetic on your calculations here, these divisions and multiplications, necessarily means there will always be some inherent noise just simply due to the fact that your computer is going to round off digits out to the umpteenth decimal place. And usually that happens when you get upwards of around 10 to the 18th here in your condition number. Oops, excuse me. So about 10 to the 18th, like so. So when that happens, it is mathematically impossible to do a matrix inversion simply due to the fact that you have finite precision arithmetic in your computer. So this is the idea of an ill-conditioned matrix or a poorly conditioned matrix here. So ill-conditioned systems blow up in the presence of noise. Well-conditioned systems are very stable even in the presence of noise. So if I have two samples here smushed together, that should intuitively make sense because the closer they get together, the closer they are to essentially being the same information, even though they may have a slight, tiny little distinction between them. But if that distinction is very slight, then a tiny little bit of error in my calculation means that slight distinction no longer has any meaning anymore. So this is why when you're doing problems like this of an inverse nature, you want your observation samples, say, to be very far apart if you can. That now stabilizes your matrix and makes it highly robust against the insertion of noise, either real world noise from a measurement or fictitious noise arising just from your finite point arithmetic.